So thank you, hello everyone. My name is Guillaume Helbecque. And I'm going to present you our paper entitled Toward a Scalable Load Balancing for Productivity-Aware Research. So to begin, a small point of context. So we just entered in June 2022 in the exascale area. Since the top 500 ranking revealed the Frontier system as the first exascale supercomputers in the world. In addition, we can note that modern systems are increasingly large, heterogeneous, and less reliable. Therefore, to tackle parallel programming on such systems, two schools of thought are opposed. The evolutionary school, which considers that traditional MPI plus X-based environment have to be adapted to exascale, versus revolutionary school, which considers that new parallel languages based on Pegas have to be developed. On the other hand, this work focuses on exact branch and bound optimization methods to solve combinatorial optimization problems. So as you can see in this figure, in branch and bound, each node representing a space of solution is decomposed into a set of children nodes representing subspaces of solution. And for each children node, we compute a bounding function, which is an estimation of the function to minimize or to optimize. And if we consider that a children node is not going to lead to a better solution, we prune it, and this way we perform a complete enumeration of the search space to optimality. So in branch and bound, we exhibit large tree size and also high irregularity due to the pruning operator. And so we have to deal with efficient data structures and efficient dynamic load balancing mechanism. So as a motivating example, we can have a look to the permutation flowchart scheduling problem, which consists in ordering n jobs on n machines such that the total completion time is minimized. And in fact, some studies demonstrate that hard PFSP instances can contain up to billions of nodes, which is huge. And so our research consists in investigating the efficient mapping of branch and bound to modern systems. Regarding the state of the art, most of the existing parallel branch and bound are only guided by performance and benefit from problem-specific optimization, like specific data structures. We also note the emergence of productivity-aware parallel programming languages like CHIUW. And more generally, there are few studies investigating the Pegas-oriented approach in the parallel optimization setting. So this work is intended to fill in this gap. In this work, we consider an asynchronous parallel tree exploration model, which consists in performing several searches in parallel. As you can see, it implies unpredictable communication between processes. And also, due to the high irregularity of branch and bound, we have unbalanced work units. So we choose to use a work-steering approach to tackle this. Globally, to each process, we perform a deep first search because it ensures good memory efficiency, and it is easily implemented using a stack in the LIFO manner. And so at the process level, the DFS is performed as the following. So we have a pool of nodes. The owner process of the pool gets a node. This node is decomposed into a set of children nodes. And finally, this set is inserted in the pool in a LIFO manner. And we do this again and again. More globally, we adopt what we call the collegial multipool approach, in which we have multiple pools in parallel, one pool per process, and so multiple DFS in parallel. And as you can see, there is load imbalance between pools. For example, this one is empty, this one not. And so we do what we call work stealing. So typically, each idle process is going to steal work items from another pool. But this raises multiple challenges. The first one is how to choose the victim and how to synchronize with the victim. And in addition, how to take into account the locality of the victim, because pools are not necessarily in the same locale or computer node. So to implement this approach, we first plan to use the Chapel's DISTBAG data structures, which implement a parallel safe distributed multipool implementation. So as you can see, this data structure, also implements a work stealing mechanism to balance workload. And this data structure is generic. As you can see, we can specify any type in the initialization procedure, and we can easily add or remove elements. So the data structure is very interesting in our context, but there is a problem, The problem is that when we add or remove an element from the bag, the pool is randomly selected. And therefore, we cannot ensure any exploration order, like TFS. Therefore, we revise the data structure into DISTBAG TFS, and we perform two major updates. So we implement work pools into non-blocking split dequeues. So typically, each pool is split in two parts, a public and a private one, using an atomic split pointer. From one side, the owner process of the pool perform a local DFS, as explained before, in a log-free manner, while at the other side, idle threads can steal work items using one synchronization point. So this scheme is interesting because it allows concurrent accesses, and it is really suitable at scale. The other point is that we re-implement the underlying work stealing mechanism. So it consists in a B-level locality-aware mechanism. So typically, an idle process first tries to steal work items locally, and if not possible, globally. The victim is selected randomly, and we steal half of the public part. So now I'm going to show you our parallel distributed implementation, but in order to better highlight its productivity awareness, I first show you a sequential version. So we initialize the root, the pool, we insert the root in the pool, and then we perform the DFS. So as explained before, we remove a parent node from the pool. Then the parent node is decomposed into two sets of children nodes, using the problem-specific branching bound operators. And finally, the children are inserted in the pool, and we do this again and again until the pool is empty, meaning the end of the exploration. So in this figure, I omitted the termination condition for readability, and because it's not the key point of this talk. Now you have the distributed parallel version, which is named P3D-DFS. So it is available in our GitHub repository. And so as you can see, the parallel distributed version requires a few more lines of codes, thanks to the task parallel features of Chapel. So here we used two nested co-forward loops, and also the on-close in order to control locality. Another point is that you can see that in the insertion and retrieval operation of the bag, we now have to specify the task ID in order to ensure the TFS. And we also have to share the global knowledge between processes. This approach is generic because the nodes type as well as the problem data and branching bind operators are given as arguments of the search procedure. And this allows us to instantiate P3D-DFS to the permutation flowshop scheduling problem, the unbalanced research benchmark, and the nQueen problems. So we experiment our approach using the HPC facilities of the University of Luxembourg. So we used computer nodes equipped with 138 cores we solve large PFSP tiers instances, as well as large synthetic UTS trees. And we perform two series of experiments. First, we evaluate the memory consumption of DISBAG and DISBAG DFS. And then we evaluate and compare the performance of P3D DFS versus MPI plus X best known counterparts. So it is worth to mention that counterparts are implementing different approaches. So first of all, you can see in this figure the bag size according to the processing time, solving PFSP instances. So first of all, using the DISBAG data structure, we can see that the bag can contain up to millions of nodes at a time. Especially in this case, we stored up to 11 gigabytes of memory, which is huge. While using DISBAG DFS, the memory consumption remains bounded over time. So this demonstrates the suitability of our revisit in the DFS context. Now, in this figure, we compared P3D DFS to MPI PBB, which is an MPI plus pthread implementation of branch and bound applied to PFSP. We consider different granularity, fine, medium, and coarse. And we can see that in almost all cases, our approach is better than the baseline. So this can be explained by the fact that the baseline implement a centralized coordinator process in the work stealing mechanism that can lead to bottleneck at scale, while our approach not. In addition, in that case, precisely, which is the largest instance with the finest granularity, we can see that the MPI counterpart is better than P3D DFS. And this could be explained by the fact that DISBAG DFS still have large overheads, especially visible at fine-grained. Then we did the same using the UTS benchmark. So here we compare P3D DFS versus MPI PUTS, which is a two-sided MPI plus MPI implementation. Again, we can note that using the medium and coarse granularity, our approach is outperforming the counterparts. Again, this can be explained by the use of a non-locality aware work stealing mechanism in MPI PUTS. But as you can see, considering fine granularity, again, our approach is outperformed. And again, this can be explained by the overheads of the data structure and also by the poor intranode speedup observed in preliminary experiments. Because I remind you that this is absolute speedup, and so the reference time for P3D DFS is smaller than the baseline. And so we have a high effect. To conclude this talk, we have seen that DISBAG DFS allows high productivity and good performance for coarser grain application. P3D DFS is competitive to MPI plus X baselines in terms of performance and productivity awareness. We plan to investigate and benchmark DISBAG DFS low-level mechanism, especially at fine grain. We also plan to extend P3D DFS to other combinatorial optimization problems, for example, the quadratic assignment problems or the traveling salesman problems. We plan to extend our experiments to larger systems. And also, we plan to develop a Chapel's distributed back DFS package module. So here you have some references. And finally, I thank you for your attention. And if you have any question, feel free to send me an email or to ask now.
Yep, we have 5 minutes for questions. So it would be great if people could raise their hands to ask. And thank you for your presentation. Brad has a question.
Yeah, I just have a couple of very simple questions, and I have to confess that I'm often distracted during this workshop by other things, trying to keep it running. So I apologize if you've already said this, but in the performance graphs that you showed, what architecture did you say that you gathered those on?
Sorry?
What system or architecture were these performance results gathered on?
So I use this hardware for the comparison.
Great. Okay. Thank you. Yeah, I did miss
So
that. I apologize.
Okay, I use up to 64 computer nodes equipped with 138 cores each.
Okay, great. Thank you. And then the one other question I had is just a very technical one. I know I saw you, and I already knew this, that you're working on trying to figure out whether this can be contributed back to the CHIUW repository. If somebody wanted to use your dist bag in the meantime, is that something that they can get directly from your GitHub repository?
Yes, yes, you can get the data structure directly from the public repository. Yes.
Okay, great, thanks. Yeah, I was just talking to a user this week who was potentially interested in that, so that's good.
Okay, great.
All right, thank you very much.
Thank you.
I had a question in the meantime, while we see if there's anyone else in the audience. On slide 18, you have graphs, and particularly for like fine, both the ideal solution and your solution deviate quite a lot from the ideal speedup. Do you have any idea of why that might be happening? Because I'm pretty sure you mentioned that you evaluated the best known solutions or in MPI and the others, and still they're kind of off. So do you have any idea why that might be happening?
Can you repeat? Sorry, I didn't understand.
Yeah. Do you have any idea of why that might be happening? Why they're so far from the ideal speedup, even the best known solutions? Especially like close to the bottom left.
The bottom one here.
Yes.
Sorry.
I was just going to say, my understanding of the question is like, obviously the ideal in life is to get the ideal speed up. What is it about the nature of these problems that causes particularly like the leftmost graphs to be so far off from the ideal?
In my opinion, it's due to the fine granularity of the application, because in that case we have parallel overheads are highly visible, So it's common to see such results at fine grain. And larger is the instance, larger is the workload, and smaller is this effect visible.
Makes sense. Thank you. Well, I see no other questions either in chat or from the audience via raised hands, and we're gaining on our first break of the day. So thanks again to the presenters of the first session, and let's start our break.